Welcome, dynamics students. In this lecture, we'll be discussing rigid body kinematics and planar motion and tackling the idea of two different rigid bodies moving with respect to two different reference frames. So today we've been looking at a single rigid body moving with respect to a fixed external reference frame, and then looking at the motion of two different points on that same rigid body. We're going to use similar tactics of defining two different reference frames and looking at how they correlate with each other geometrically, but instead of applying that to two different points on a single rigid body, we're going to look at the motion of something on a single rigid body with respect to the other reference frame, which could be another rigid body. So to do that, we're going to just start out with what we are already used to working with. A couple of rigid bodies, so we're going to look down at our diagram. We have a body F, which is same symbol, so we can think of this external body as maybe an inertial reference frame that we would use to relate acceleration to force, or another rigid body. And then we have our, what we might want to think of as our moving body B out here, and we've defined coordinate systems for each one. So we've got X and Y, so X hat and Y hat, or I hat and J hat, you can think of for body F. And then we've got X prime and Y prime, which is the coordinate system. It's still rectilinear, rectangular coordinates, but it's specific to body B. So if you move, 5 feet in the X direction and 10 feet in the Y direction with respect to body B's coordinate systems, you won't necessarily have moved that same distance over here, or you wouldn't end up in the same place, relative to the X and Y. But we can relate the two coordinate systems, especially if we define some line somewhere in body B, like in this case it's X prime axis, as having some angle with the x-axis of body F. This theta angle becomes kind of like the linkage between the two coordinate systems. And we can just use plain old trig to relate our x prime hat, our x-axis in body B's coordinate system, to the x and y axis of body F, and likewise with the y prime coordinate of body B. So now we have two rigid bodies, each with its own coordinate system, and a trigonometric relationship between the two coordinate systems that we're familiar with. It's defined by some angle that body B's reference frame is making with body F's reference frame. Okay, and if the body B is not rotating within its reference frame rotation is the same as its own. So we'll use that later. So we kind of have position nailed down now. We're talking about position in terms of an x prime, y prime, correlating through our cosine sine relationship with some position in our x hat, y hat, body F coordinate system. Now we want to look at velocity. So take the first time derivative. So we're going to start by taking the first time derivative of position, in body B, and we're going to start with our x prime hat. So our x coordinate in the body B reference frame is x prime in the x prime hat direction. Take the first derivative with respect to t, we can call that x prime hat dot, as if we didn't need more symbols here. And so that involves just taking the first time derivative of these two expressions, and we'll end up with first time derivative of cosine theta equals negative sine theta times d theta dt, and time derivative of sine theta is cosine theta times d theta dt, and the d theta dt is our theta dot here. Well, if we compare that to our expression for y prime hat, we notice that what we've got right here is in fact y prime. And this follows our general observation that when we look at the rate of change of any kind of unit vector, we get something that's 90 degrees to it. So its direction of change is at right angles to whichever direction it was going. So our dx prime hat, or the first time derivative of the unit vector for body B with respect to time, is the rotation rate of the angle that body B's reference frame makes with respect to body F times the y-coordinate unit vector for body B. Switcheroo. So we can do the same thing with our y prime, looking at the time rate of change of that y-axis specific to body B's reference frame. And we get something that's basically the opposite with a minus sign by relationship with our sine cosine first derivative relationship. So we end up with a negative theta dot, or omega, rotational velocity of our body B reference frame with respect to our body F reference frame. And now we've thrown out the other unit vector. Okay, so now that we have these relationships, let's take a look at what would happen if we had some arbitrary vector t here in body B, or in its reference frame somewhere. So it's looking like it's almost parallel to the x-axis. So we're gonna denote it as having some length t sub x in the x prime direction, and some t sub y in the y prime hat direction here in body B. So in the case of the one we drew, t sub y is pretty small, and t sub x is practically equal to the magnitude of t, just, you know, as something we could draw. It could be any vector in our body B, or in the reference frame that body B is occupying. Okay, let's take the first time derivative with respect to time in body, changes in body F, or body F's reference frame, of this vector that's only in the reference frame of body B. So we're going to take the first time derivative of vector t referenced to the body F reference frame. Okay? Typical derivative of a product. So we're going to do the first derivative of the length of t in the x prime direction. So that's t sub x dot directed in the x prime hat, plus, now we're going to do this as our u dv plus v du. We did the du, now we're going to do the dv. So we have our t sub x times the first time derivative of theta hat prime with respect to the F reference frame. And we're going to do the same thing with y. We'll get, you know, same kind of expressions. And then we're going to collect terms based on reference frame. So when we look at t sub x dot, that's the time rate of change of the length, this length, in this reference frame. So t sub x dot is how fast the vector t is getting longer parallel to x prime hat. So it's squarely within the body B reference frame, and the same thing with this. So if you put these two together, what we actually have is the time rate of change of vector t, capital T, within body B, reference to the body B's reference frame. So these two are the x and y components, or x prime and y prime components of this vector. Now what about these other two? You know, we can recognize a length t sub x and t sub y, but now we've got this first time derivative of the actual axes, coordinate axes of body B with respect to reference frame F. Well, that's what we already derived up here when we took a look at how these position vectors change using our trig functions correlating the reference frames. So we can drop these expressions in here, because this is basically saying how fast is the reference frame for B itself changing with respect to the reference frame of F. Good thing we have such a nice, neat expression for it with a nice angular velocity. And we'll collect terms and substitute in these theta dot expressions, and we again get our velocity effectively of t within beta. So how fast is something changing with respect to the beta reference frame, plus the angular velocity of the beta reference frame with respect to reference frame F times this set of terms. So we still have something that's a little bit hard to wrangle. So we're going to use the properties of the cross product and just kind of notice that this whole collection of terms could be expressed in terms of our angular velocity in the k-hat direction crossed into, which it already is because we're talking about planar motion. Let's do a little look back. If this angle is changing, it's getting bigger with time or something like that. If you think about it, the vector direction for that angular change is going to be pointing out of the paper, at least for that counterclockwise direction. So our theta dot was already in the k-hat direction, so we're just basically acknowledging that. So we're re-expressing the term in the circle here as a cross product. And we're getting a little change in our signs here because that would change in executing the cross product. So this makes it a little easier because then we can recognize this term just simply as vector t. We're right back up here. So we have the length of t in the x prime hat and the length of t in the y prime hat. And we have our rotational velocity of reference frame B with respect to reference frame F crossing into that. Now this looks pretty familiar. This looks quite a bit like the velocity of one point on a rigid body if we know the rotational rate of that rigid body and then the length of a vector from one point to another point for which we know the velocity. This is really similar, and we've used a similar strategy for doing the derivation. But this time, rather than looking at 2 points in the same rigid body, we're using that same rationale to correlate what's happening with respect to one reference frame versus another. So here's our final expression. We can say the time rate of change of some vector in the reference frame of body B from the perspective of reference frame F is that same velocity from the perspective of reference frame B, where it's all happening, plus the cross product of the angular velocity of reference frame B with respect to reference frame F. So now we're looking at a reference frame rotating with respect to another reference frame, crossed into an expression for that vector that's changing using units within reference frame B. We're using our x prime units. So effectively, if you think about it, the angular velocity is acting like a coupling between the two reference frames. It's giving us a link, so we can think of it as a way to map what's happening with one reference frame to what's happening with the other reference frame. So we're going to kind of expand on that idea a little bit. And so we're going to imagine some point, some particle P or some point out in space that's moving on some crazy path. So we got point P moving on a path here. And we have two different rigid bodies out in space looking at P. And each rigid body has to have its own reference frame. So if we're going to look at point O and point O prime, we better give them their own reference frames or we're going to violate the rules for relative motion. So if we want to look at the motion of point P with respect to O, we're going to have to do some kind of mapping the way we did with with our body B and our body F in our previous expression that we just derived, to kind of look at how is P moving with respect to O prime. We can't just use the motion with O. So we're going to look at P versus O in reference frame F, P versus O prime in reference frame B, and then O to O prime, which will give us an idea of what the two reference frames are doing relative to each other. Hence, you'll hear relative reference frames. So we're going to have to deal with the fact that we could have relative motion between these two rigid bodies. So we're going to start with some vector addition. Good something that we can't get confused on, hopefully. We can definitely, for any point in the motion of P along its path, we can draw a radius vector from point O to P. We can draw a radius vector from point O prime to P, and we can certainly draw a radius vector from O to O prime. We can draw those radius vectors anytime, and we can add them up. They're going to follow the laws of vector addition at any instance. So ROP equals RO prime plus RO prime P. What do we do when we want to look at the velocity of anything? We take the first time derivative of position. Hey, we got this great expression for position that includes, basically at reference frame F here, reference frame B, and then some between them. This could be promising. So let's take the first time derivative of this vector addition expression from the standpoint of reference frame F. So that's what this little scripty F up here in the corner is. That's to remind us that we're taking that time derivative as if we're standing here in reference frame F looking at how everything moves. And that basically says whose unit vector has to get changed and whose doesn't change with time. So any coordinate system that I create in F, say I have an ij that's specific to F. If I were to take the time derivative, I and j wouldn't change. But if I had, unit vectors a and b over here, if I'm taking the time derivative of a and b unit vectors with respect to the F reference frame, these would change with time. I'd have to have some expression for them, similar to what we did with the x prime, y prime in our previous example. Okay, so we'll get rid of this for now. Okay, so we're going to truck through and take derivatives with respect to time, just apply some math. So first time derivative of radius vector OP from the standpoint of reference frame F is going to be equal to the first time derivative of radius vector OO prime from the standpoint of reference frame F plus the first time derivative of radius vector O prime P from the standpoint of reference frame F. Okay, this is obviously going to be our difficult one because it isn't really obvious. So we can kind of rename these. If I'm looking at the time rate of change of this vector from the standpoint of what's effectively its own reference frame, well, that's just the velocity of P with respect to reference frame F. That's what the slash F is. Likewise, this O prime, if you're standing here at O, the time rate of change of this radius vector is just the velocity of this point with respect to reference frame O. So you're standing here, this guy is getting, if this body's moving this way, this is positive in the right direction. O prime's getting further and further away from you. And if we look at this guy, we can basically just rewrite it a little bit simpler. We haven't really changed it. We're acknowledging that we're taking a first time derivative, which radius vector we're taking it of, and we're acknowledging, hey, that we're taking that with respect to the reference frame F, whatever that ends up being. Okay. So rewrite again, and let's investigate and see if we can't, maybe find a little bit better way to simplify this. So let's zero in on on this term and see if we can't use the rules that we already know, the ones especially what we just derived up here, to maybe give ourselves, as I scroll along, we're going to invoke that equation that we just derived and see maybe there's some better way of expressing this, because we can't do a lot with this r prime p time derivative with respect to a reference frame that doesn't involve really p or o prime. Okay, well, let's use our other expression that says we could say that this is the first time derivative of our o prime p with respect to the b reference frame. Okay, now that's understandable. That's like saying you're standing here in B and you're looking at how fast this vector changes with time, looking at point P going along. That does make some sense, and in fact we could call that basically the velocity of P with respect to B. The same way we called this expression the velocity of P with respect to F. We're looking at P from the point of view of B, just like we looked at P from the point of view of F. You hear that term point of view a lot. Okay, so we got a solution for that term. We had to add the angular velocity here, first time derivative of theta, and in this case theta is the angular velocity of B with respect to F, because that's what we're relating in this case. We've got this time derivative of something that basically exists between P and B. We're trying to look at it from the standpoint of F. Remember what we had back up here. We're kind of back to the same situation. We're relating B to F, so we're having to involve that angle between the two reference frames. So it isn't just any theta dot, it is the theta dot representing the angular velocity of B with respect to F. Okay, and then we're going to just cross that into the radius vector O prime B. Basically, I keep flipping here. It's the same thing as what we had with T. So we're just applying this to our first time derivative of O prime to P from the point of view of reference frame F. So now we got something that's a little bit easier to deal with. Like I said, that'll give us the first time derivative of R with respect R between O prime and B with respect to B is just VP, velocity of P with respect to the B reference frame, plus omega, angular velocity of reference frame B with respect to F reference frame F, crossed into that radius vector, this other radius vector O prime to P, just a positional vector. So we're going to take this whole shebang, remember, was this term. So it's going to add on to our V O prime P and VP with respect to F. So we're rewriting it down here on another line. So the velocity point P from the point of view of the F reference frame is the velocity of O prime with respect to F, which is kind of like saying the velocity of the entire reference frame B with respect to reference frame F. So how fast is the B reference frame moving with respect to F? Not rotating, just translating. So this is translational motion of B with respect to F. Because point O prime is in B. If we're talking about translation, every point in the body moves together. Then we've got the velocity of our point P with respect to the B reference frame. So we got another two velocities there. Then we got the rotation of the reference frame B with respect to F, and we've got the length with the direction of radius vector O prime to P. So now we can see we're setting up to relate not only the velocity of something within a given reference frame, but the velocities and rotations of one reference frame with respect to the other reference frame. And in fact, we're going to take this term and this expression together and look at them as its own particular velocity. What this is saying, if we put these together, is we're saying that this is the velocity of, with respect to reference frame F, of some point in reference frame B that just so happens to correspond to point P. So it's like we took point P and we made it like a little tag onto reference frame B. And we said, okay, we're going to look at the entire movement of reference frame B tracking the tag that is point P. So that is the point of interest in reference frame B, not just any point in reference frame B, but point P in reference frame B. So think about it as the whole reference frame moving, but we're just looking at one point in it. So kind of esoteric concept. So let's use a very concrete example to try to apply this. And just as a hint, relative reference frame problems hinge on figuring out what body or bearing surface or point on another body to assign as its own reference frame or as a point of contact between reference frames. So we'll apply basically, let's erase a little bit, we'll apply this equation quite a bit that we went to no small amount of work to derive. But the trick in applying it is to get in your head, okay, who's reference frame F, who's reference frame B, and who's rotating with respect to whom, and all of that. So that's, again, the real crux of the problems, and identifying those things just takes a lot of practice. But the vector algebra, the relationship between the reference frames, the time derivatives is just totally basic math. Okay, so let's look at an example. So we've got this slider block B, and it's traveling back and forth in some kind of slot. We've identified an IJ reference frame, and if we're going to apply the right-hand rule, we can say that our positive angle of theta would be counterclockwise. So that block is being pushed by a rotating rod. And so we've identified point Q on the block is the point on the block that happens to be contacting the rod. It's only contacting a one point, but it's contacting the rod at a particular snapshot in time we're concerned with, which happens to be when this angle is 60. So rod's rotating in some negative omega because it's going clockwise, I think. We'll have to see which way it's going. Yep, clockwise. And so at that instant in time, point T somewhere on the rod happens to be contacting point Q somewhere on the block. So point Q and point T are in the same position relative to this reference frame that's the bearing and the hinge, kind of the support structure for the whole thing. You can think of that's bolted to the floor, the wall. It's not moving. Rod R is definitely moving. It's rotating. Block B is translating here. The supports that we've crosshatched, they're sitting still, so to speak. So it makes a lot of sense to consider those to be our reference frame F, the fixed reference frame. And then we're going to have rod R and body B be two different moving bodies within that fixed reference frame. So we kind of got two. We don't just have F and B. We have F and R, and then we got R and B. So the key is to use this instant in time in which we have a point of interest P that corresponds with T, and so we end up saying, well, T and Q are the same, and we're going to use point T on the rod the way we used point P as the tag for reference frame B in our derivation example. Okay, so what somebody wants to know is what is the velocity of point Q with respect to right here on our moving block B with respect to the reference frame F of the slot when theta is 60. Okay, so I'm going to step through this and I'll just slide back and forth and refer to the figure as I need to. So as I was saying, ground and the slot are going to serve as our sort of our fixed reference frame F. The rod is a second reference frame. We'll call it R. This is going to be kind of like B back in our derivation. So we're going to need to find the velocity of Q with respect to the fixed reference frame, you know, the bearing reference frame we'll call it. And we can say from the equations that we've already derived that the velocity of Q with respect to the rod plus the velocity of Q in the rod with respect to F are going to add up to the velocity that we need. So we're kind of using different labels to apply what we did before. So again, velocity of Q in R. So this is the velocity of point Q in the rod reference frame, or you can think about it if you are on the rod and you're looking at how fast point Q is moving relative to you, it's going to kind of look like it's moving along the rod in a certain direction. And if we go back up here, if you can think of the rod as turning this way and you're standing on the rod and you don't realize you're rotating, it's going to look like point Q is just moving straight back and forth in the radius direction of the rod. So that's the velocity of Q in R. The velocity of the rod in F is purely rotational. So that should be something that we can handle. So again, velocity of Q as a tag point of R in F. So this is, and now this term here really is analogous to this, except we have R and T. So we're using point Q, which is the same as point T, as a tag to say how is the rod reference frame moving with respect to the F reference frame, because at the instant we're talking about point T on the rod and point Q on the block are the same point because they're in contact. So that's how we go from having effectively 3 bodies or 2 bodies in a fixed reference frame to really only working with the rod versus the fixed reference frame. So we'll continue with that. So let's focus on this term. When we finally figure out how point T is moving with respect to our bearing reference frame, we're going to end up saying, okay, we're going to look from T to R, and we're going to want to know how, from T to Q, the 2 contacting points. And say, okay, how is Q on the block moving with respect to the rod? And the answer is it's moving back and forth along the rod, which is a little bit hard to imagine. But basically it's point Q can be thought of as it's going to slide up and down on the rod, or the rod is going to slide up and down on point Q, as the case may be. So we're just going to give that velocity a magnitude and say we know that because it's directed along the axis of the rod, it has to be in the direction of the rod, which is this expression. So point Q is sliding along R, so it has the same orientation. We don't know what direction, if it's sliding towards O or it's sliding away from O. So that'll just change with the sign of VQR. Okay, so we can look at the velocity of point T, which is the contacting mirror image of point Q on the rod, and say, okay, how is point T moving with respect to the fixed reference frame? Okay, this is our tag point on reference frame R. So what we're really looking at is, well, how does reference frame R move with respect to the fixed reference frame as seen by the motion of point T, which is sitting in R? Okay, well, the rod's rotating, right? So what we're looking for is the velocity of some point on this rod. So we can look at that as pure rotation. So we know the rod is rotating at -10 radians per second because it's clockwise, and positive rotation is we defined as counterclockwise. K hat, obviously planar motion, so rotations come into or out of the screen, crossed into the radius vector from the point about which we're rotating, our position that we know the velocity of, which happens to be 0 because it's a pivot point, to t. So r from O to t. So again, this is super simple. Now we're back on a single rigid body. We've jumped onto rigid body R, and we're just looking at the relative motion of point T, which is the contact point to Q, which we want to know the motion of, versus our pivot point. Velocity of the pivot point, 0, so we only have the rotational component. So really the most complicated expression is that radius from O to T, having to remember we've got to do a little bit of trig because we've effectively got the the opposite, and we need the hypotenuse to get our x component, our I hat component. So obviously we've written this as from O to T, so we are going negative in the I hat direction, positive in the j hat direction. Okay. So our body B, it can only move in the I hat direction versus the reference frame F. So we know that Q, the velocity of Q with respect to reference frame F, which is what we were looking for in the first place, is some magnitude directed in the I hat direction. I hat is fixed in reference frame F, so it ain't changing with no time derivative. So we can keep that unit vector and know that it isn't going anywhere. So let's look back and see what we've got. We have two equations. We have this one, which gives us some relationship to our magnitude, and this expression up here. So if we distill all that down, we end up having two unknowns: the magnitude of the velocity of Q in the R reference frame. How fast is Q sliding up and down R as R moves? No rotation from the point of view of that point. It doesn't know R is rotating. And then the thing that we really wanted to know, which is the velocity of Q versus the fixed bearing reference frame. And so we have two equations effectively coming out of what we have here that we can use to solve that, incorporating what we already know from these other two equations. So we'll just break that up and work through the math on this page. So we can say that in the I hat direction, V of Q with respect to F, which only has an I hat component, we can equate that to VQR negative cosine 60 I hat from here, the I hat component of this. And we're just building up this expression. So we've taken the I hat component of this, and now let's snatch the I hat component of this, which is, we'll have to work out the cross product. It'll end up coming from that component. So we have contributions from I hat to I hat to I hat. This was coming out of our cross product. And so we have 0 equaling this plus this, so we can solve for VQR by just equating these two terms. So again, just solving two equations and two unknowns. So we end up from our j hat terms, and this is j hat in the fixed reference frame. Remember, this is the bearing reference frame that has the hinge and the slot. We find that VQR is actually negative. So let's see how we define that back up here. We had defined VQR as going in the negative I hat direction, so we had assumed that it was going kind of out this way. It's actually going back the other way. So from the standpoint of the rod, if you're standing on the rod and you're looking at point Q is going to appear to slide this way relative to you. If you were standing there, you'd just see Q going this way. because you don't know you're rotating at that point. And then we can solve for what we were asked for the velocity of point Q on block B with respect to the reference frame. Fixed reference frame is 26.67 feet per second. So we can take a look at that in terms of adding up all those vectors, right? We have the vector Q sub r directed back towards the hinge along the rod. We obviously have our Q with respect to the reference frame F going straight down the slot, and then not surprisingly we have the velocity of point T with respect to F is directly perpendicular to the radius of the rod, which is exactly what we would expect for tangential velocity of a rotating rod. So everything's really pointed in the way you would think it's pointed. And it all kind of adds up and makes sense, and we can even do a little vector addition, dropping in the expressions that we've just determined for the magnitudes of each of these, and show that they all add up by vector addition, which is very reassuring. So let me zoom out a little and just kind of go over what were the key points. First, we leveraged this expression that we just derived to relate motion of a point from the standpoint of one reference frame, we'll call it a fixed reference frame, with respect to that point's motion within a moving reference frame, another reference frame, and then a collection of one vector and a cross product that describes the motion of our moving reference frame with respect to our fixed. And the key to that was this concept of the tagged motion of the moving reference frame. And so the velocity of our tag point in our moving reference frame from the point of view of our fixed reference frame. So that's how we used points Q and P. Really it was, or excuse me, Q and T. Point T was really our tag point on our reference frame R. And then we used a secondary concept that, well, hey, wait a minute, point T and point Q are coincident. They're at the same location. And we did a secondary evaluation of, well, wait a minute, what would the velocity of point Q with respect to point R be if we were standing just in R? So we kind of double leveraged the idea of relative reference frames. We looked at the relative motion of B and R, and then we used our derived expression to look at the motion of tag point T in R with respect to fixed reference frame O. So you will probably get tired of hearing the term with respect to, but it's totally essential. And you can see we have one fairly simple expression for vector velocities and angular velocities of a couple of rigid bodies, and using that we were able to confidently solve for something that otherwise might have been somewhat complicated. So these do have very powerful applications in dynamics, the idea of relative reference frames. So stay tuned. We'll conclude our study of rigid body planar kinematics with the next lecture, which will one-up what we just did, take the first-time derivative, and look at relative accelerations of two different rigid bodies in their own reference frames. So stay tuned.